Okay, so the homework over the weekend was to calculate or sum all those residual values together. So that's kind of what I'm hoping you did. But before we actually move on for today, I want you to review in your groups what we actually did on Friday. What is a scatter plot? What is a residual value? How did we get that line or that prediction line, that equation, that model? It is all up on the board here. This is the model that we created on Friday. This is our actual scatter plots. And I want you to talk about those vocab words. Summarize what we did. How did we find this model to represent this data? So I'm going to give you 2 to 3 minutes just to summarize in your groups. And I'm going to be walking around and listening to the things that you said.
Okay, so the line goes through like 2 points.
How did it actually come up with
Which
line? There's not prediction models. That's going to be the residual value. But how did I come up with that equation to represent our data? Very good. And how did we find the slope?
I don't know what that is. I know we have the.
Yeah.
Yeah. Very good. I did. So what are all these things? What is a residual?
That's the error from a line to a data point.
Very good.
Try to write it down or something.
Just
See if I have it.
Look, I'm calling. Tell me what a residual is. So how did I find that linear model?
The linear model.
Well, no, we just chose the 2 points.
And then we
Calculated the residual.
well, once we picked our 2 points, what did we use to create our actual equation? What are the 2 things that we have to find?
We use the slope.
Yes. What is that?
I forgot what it's called. Oh, the slope. Same thing.
And the line.
And then we calculate the y-intercept.
I don't know if I got this. I'm not sure if I got this.
Okay, how about we put all of this away, and then you can look at Danny's. Okay.
Danny. You're the second person I know who's named Danny.
Okay, so I heard some good things. Number 1, residual. Lucky. What did you
Residuals.
tell me a residual is?
I said residual is the error from a line to a data point.
Very good. This line that we drew in, this doesn't represent every data point. This is a model that we created to help us predict future data values or interpret how close our line is to actual data points. This red stuff right here, those are all the residual values. It's the distance from the data point to our prediction model. How did we actually get this model, Emily?
You chose the 2 points from the scatter plot.
We chose 2 points from our data set on our scatter plot, and then we drew the line through them. What did we have to find to actually write this equation? What are those 2 things that we were looking for?
Slope.
Say it louder.
Slope and y-intercept.
Perfect. We found the slope and we found the y-intercept. Now we have a prediction line for this data set. Is this line perfect? No. And over the weekend, when you were actually finding the sum of the residuals, you should have found that the sum is 5.3 repeated, or 16/3. That's all of this red distance added up. What do you think this sum tells us about our model? As a group, talk about it. what do you think that sum tells us about our model? Discuss that question in your groups.
Like, would it be the average?
Yeah, like that.
Different in many ways.
Could be different. What do you mean different in many ways?
It could change over time, like it could become more, increase in size or decrease.
I feel like if I had more data points, I like it. Very good, Randall.
Like showing you
How close all of them are to the line, and how close it is to being an actual. What?
What did you say?
I said, it may be like how close the points are to being an actual straight line. Is that good?
Max,
Yes.
can you tell me what you said?
The residual values are telling you like how close like all the points are to being an actual straight line, to being a line, like how close they are to being an actual line.
Well, if all the points were on the line,
That'd be
then
that
the
no
sum
line.
would be,
It'd be a line if it.
it'd be a line.
Yeah.
It'd be 0, because there'd be no error. Well, in real life, there's error. Not everything is perfectly linear. We write these equations to model situations, but it's not perfect. Is this the only equation that we could have made for this data set? No. Could we have chosen different points and drawn a different line with a different slope and a different y-intercept? Well, in general, we want the best representation. How are we going to get the best model?
Trying to find a line that can go through the most points.
That's what somebody said in my last class.
That's what I would think.
I would think that too. The more points on the line, well, then you have more points with a residual of 0. That's good. But that's not always going to happen. A line is when there's constant rate of change. When I'm looking at all these points, where I draw them, there's no two places where they're going to have the same rate of change. So that is not possible for this situation. But we have a tool. There's a tool that we can use to find us the best linear model. What tool do you think that is?
Graphing calculator.
It's a graphing calculator. If you have your graphing calculator, take it out, and I want you to take everything else off your desk. Whoop, hold on. Raise your hand if you need a graphing calculator. We're going to use one per pair. So, Jardo, if you could go sit over there, that'd be perfect. You got one? You guys all have one? Perfect. You're going to share with Randall. Okay? You're going to share. You're going to share. You guys can use this one.
Actually,
And
make her think.
share.
Let me help you.
Awesome. You guys are on it.
I called you Randy. I called you.
Mine's a color.
So,
Let's have you two are going to share and you two are going to share. Okay? Okay, and then I have my own calculator. And I'm first going to show you some important buttons that we are going to be using before I actually hand out the directions. Yes?
Mine's black right there. I colored it.
I did magic some. There was another one, but it's not tonight's homework, so
That's going to be
I colored it.
okay. Thank you. No problem. Okay, here is our very beautiful graphing calculator. And I have it on the backboard as well. I drew that just to kind of give a representation. The important buttons that we are going to use. Before we actually press any of them, we're just going to identify them. The second button, that's the blue one. We're going to be using that as well as, see this y equals button? Above it, what word does it say? Stat plot. What color is it in? Blue. In order to ever get anything that is written in blue, you have to press the second button first. So eventually we will be using that combination. Another important button is the zoom. That is another gray button. Notice the zoom is not in blue, so you don't have to press the second button first. Another important button is stat. Stat is next to, it's 2 away from the alpha button, which is in green. So have we just identified where those buttons are?
Yes.
Okay. So now I'm going to hand out the directions. You are going to be creating a scatter plot on your graphing calculator. And in your graphing calculator, just like what we did, it's going to create its own model, but the calculator creates the best one. Now, we're not just going to take the calculator's word for it. We're going to justify why it's the best, but first we have to actually find what their best model is. Are you ready to do that?
Sure.
Okay, here come directions. And we pass them out. Can I move to the side? 2, 3.
Did I tell you about my new lifestyle choice? Vegetarian now. Are you serious? I've been vegetarian for 4 days. Why? I don't really know. My mom's been like vegan for years. She's always happier with me and like she feels healthier and stuff. So I thought I'd
Okay, Lene has offered to actually do the problems on the calculator at the board. So we're going to help her out with her directions. You can follow along with us, or you can try and do this on your own. So first thing, the directions say press stat. Look at the green.
Next to the durable button.
Perfect.
Why not?
Then it says hit edit. So your edit's highlighted, so we're going to press enter. Now it takes us to these lists. These lists represent our independent and dependent values. So under L1, we're going to type in all the independent values. What is our independent unit?
Age.
Age, very good. So type in all the ages under L1. You would need to dig it up. To type in the data, you need to press the number and then enter. So I would do 6. That's the first age, then enter. Make sure you... Alright, now you can type in there. If you're showing fresh.
I need to get rid of them.
You got stuff there already?
No, no, I accidentally put 9.
Go to L2. I don't want to go to L2.
And try working with things. Yeah. This is a new tool. I understand that this is not something you are used to doing. We're figuring it out together.
She didn't tell us to do
Once you have all your independent data listed, see those arrow buttons? You press the right arrow to get to the right list. So under L2, we're going to type in all our dependent information. What letter represents the dependent? X or Y? Y. Y is our dependent information. What's the unit that we're using in this scenario? Shoe size. Very good. So we're entering all the shoe size into L2. Lene, you are doing a great job. And check in with your partner. Make sure all their information is correct, that they have all the right coordinates. Wait, check each other.
That went wrong.
How are we doing?
Why'd you start at 8?
Good?
Where's that?
We just realized that was there.
No,
Data is entered?
I just didn't. Oh, it's recorded? Okay.
Perfect. Okay, looks like everybody has their data entered. Well, that's great. So that's just your list of information. Now, what are we actually looking for? What do we want to see on our calculator? The graph. We want to see that scatter plot. So in order to actually see the scatter plot, we have to turn stat plot on. That's what it stands for, scatter plot. So the scatter plot is in blue writing, so we have to press the second button first. So you're going to hit second, and then the y equals button. Second, y equals. Very good. Okay, now Linnaeus is already turned on because it says plot 1 on. Well, most of yours is probably off. So what you're going to do is hit enter. And then you want the on to be highlighted. So in order to do that, we have to hit enter. Enter kind of makes that thing highlighted. So that's turning your stat plot on. Is anybody having trouble? Checking in with your partners? You guys are doing great. Okay, once it is on, hit second and then mode, because that gets us out of there. That second quits. Okay, and then what do our directions say after we get out of there? What button do we press next? Randall? Zoom. So hit zoom.
Now I was supposed to. I think I broke it. Did you just go blind?
Yeah.
So did mine.
Now it's on.
That's, yeah, I was supposed to.
Broke it. Okay, now
That's hers at that time.
press the zoom button. Where's zoom? Nice. And then it says to press number
Actually, really easy.
9.
Another try. Oh, okay.
Enter.
I feel like I should hear some ahas once we hit zoom 9.
Yay.
Aha! Did you hit 9?
No.
Aha! Oh.
I don't want to draw a line. Don't they call it? I said,
So that must it's just because it's on and you don't know.
Wait, this
Oh,
you are.
thank you. 9. Yes. Hit enter.
I want to click 9. Wait, why do we have to click 9?
That means your stat plot is off. So I'm gonna go. We're gonna look at stat.
Click enter again. Click enter again. Click enter.
So you have a 1 here.
Just click it.
So I think everything got entered wrong. So you're just gonna re-enter your data. I'll do it for you real quick.
Thank you.
Press the zoom.
Then I'm gonna delete that.
Now go down to zoom stat.
Thank you.
Beautiful. Once you have your actual scatter plot up coming, I want you to just make a little sketch on your worksheet so that you have that reference permanently. So make a sketch. It's not perfect. It's just a sketch onto your worksheet. It also asks for a title. Come up with a title with your group. Having trouble?
Okay, my title should be shoe size, no, age,
Does that look anything like?
shoe size.
Well, I didn't do mine as boxes, anyways.
A title can be average shoe size.
So,
Alright, I went out to California Pizza Kitchen.
up on our big calculator, it said error, mismatch. That told me that in my lists, my coordinates weren't matching up. I had one data point that didn't have an output, one x without its y. So then I just went back to the list and I double checked all my points. And Lene, what did we see that was missing? Yeah, there was one 8 value missing, so I just had to retype in my data. Now you can go to second quit. Right next. Perfect. And now, Lauren, can you help her with the actual graph? Is that what was happening to you?
Okay, so you go to, wait, Kate, you go to
After
you clear it.
It's Zoom then.
Yeah.
There's a caramelized peach.
That was there. And that's no problem.
Okay, so it's like salad, lettuce with onions, and then it had cooked pecans with gorgonzola cheese and caramelized peaches. I was like, I would have never tried this. It was so good. And then she has like Latin burgers, and she has this non-chicken.
I'm gonna get rid of that in the L3 and just clear that in case there was a problem.
Go down.
And then let's relook at our data. When we have a point, 6 is the 4 right next to the 6. So maybe we have to retype in our data. And I can clear it. Enter. So now you can just retype it all in. And that happens. You know, when we're using new things, sometimes we type things wrong and we learn from it.
Oh, batteries. I just realized that what's called a dependent.
Why?
Shoe size depends on the data.
Yes. Like, we
realized
really can't control our age. We can't really control our shoe size either.
But it depends on the data.
As we
See,
get
if you break your
older,
toes
our
and
shoe
cut a hole in your
size
foot.
Should get bigger, yeah.
Now, did it happen to me?
You think that's funny? There's actually a town that does that.
Staring at my dad and my
Is it?
Okay, so what we have so far, we have our scatter plot. That's what we created yesterday. So right now we are no different than Friday. Now we are going to allow our calculator to find the best model to represent this data. To do that, we're at direction 3. So as a group, I want you to read the directions and then see how we can get that best linear model. Work with your partners. Help each other out.
What are you supposed to do? I spaced out.
Number 3.
Number 3? Okay. The calculator fits a stat and calc.
I don't know where calc is.
Is yours like
Just
turned
off. It just did not turn on.
it turned off?
There you go.
Once again, I feel stupid. What are we supposed to do?
Stat then calc.
Let's try again.
I did
Go to
that already.
stat.
I did that.
Stat
You
calc.
need to scroll
calc?
over to calc.
Number,
See at
and go
the
down to
top?
4.
Yeah.
So press the right
Oh,
arrow.
okay. Alright, there
Go,
you go.
help each other out.
Am I supposed to hit enter?
Okay,
Number
so
4.
Lena's going to do it up here. She's going to go
do we just
to
hit 4?
stats.
Nope, just hit the number 4.
Yeah, we did hit number 4, and then this happened.
Then this.
Because you didn't hit
That is
yes
stat
to the
plot. That's
thing.
what a lot of
How do you
people
go
have been
back?
doing.
Oh my god, I told you.
Stat plot is
No, 'cause
different
it's
than
second.
just stat. So we are statisticians. We're given data and we're creating models to represent that data, just like you would in statistics. Stat is by the alpha. And then you need to get to the calc. So you have to press the right arrow button again. So press that right arrow to get over to calc. Now, do you see where it says lin regression, quad regression,
Number 4.
exponential regression? Regression is not just linear. There are many different types of equations that can be used to represent data. This equation, or this actual data, this looks more linear than other types of functions. What does exponential look like? What does it look like, Chris?
It's like a curve.
A curve, very good. It can be decay or it can be growth.
Supposed to look like.
What are some other types of functions we know?
Because yours is acceleration.
Linear, yes. If it's a line, it's linear. Does anybody remember some other ones? It's okay if you don't.
Absolute.
Absolute value. What does absolute value look like? A V, very good. And there's one more that I think we might know. Cubic, fancy, very good. That's what you're going to learn more about in Algebra 2. Cubic is like a squiggle kind of.
Quadratic.
Quadratic, that's what we're going to learn more about next chapter. What does a quadratic look like?
It's a U.
Yes, it's that U shape, which we call a,
Parabola.
what is it? Parabola, very good. Now I think looking at this data, this most looks like a line out of all of those shapes, which is why we are going to hit number 4 for linear regression. And then some of you just have to hit enter right away. If your calculator looks like Lene, she has to scroll down to calculate. You got a linear model. You got a linear model.
Wait, so how do I put in L2?
Sean, can you help?
Can I have to go through?
You got a linear model.
Oh. Wait, just kidding. Wait, why is mine like this?
Okay, hit enter. You got a linear model. How we doing? You just have to hit enter.
Yeah, I just didn't hit enter.
So as we're typing this on, I'm looking at everybody's different calculators. We all have different calculators, but it's spitting out the same exact equation. That's because we have the same data set, and your calculator knows that this one is the best. What's a little bit weird, we have y equals ax plus b. What are we used to seeing in front of the x? What letter? M. Your calculator has substituted a for m. It means the same thing. The coefficient of our variable represents our slope. So in this case, our slope is 0.470588235. On your worksheet, what do I ask you to round to? 100. The 100, so we need to be precise. We all need to round to the hundredths place, which is how many decimals? 2 decimal places. So I should see everybody with the same slope, the same A, and the same B. What does the B represent?
The y-intercept.
The y-intercept, very good. Then Randall has his equation written in the circle. That is perfect. That's what I'm hoping everybody has. Perfect. So you can write your equation right there.
Your equation is 0.5.
Good job. I can totally do this, but you did it here.
Oh, right over there, 100.
Okay, so at this point, this is the equation that you should have written down in your little circle to represent what our model is. Now, thinking about this model, is this exact? Is this going to tell us somebody's shoe size based on their age?
No.
No. What is it used for?
The average.
Maybe an average. It might help us predict what a shoe size could be, but it's not perfect. Am I the average height of a 27-year-old? No. So I probably can't be modeled by an average equation.
So say this was like a shoe size line. Would you be one of the dots that's off the line? I got it now.
Would I have a low or a high residual value?
Or do you have a really high one? You'd be off the chart, right?
Because I'm more error. I'm far away from the average 27-year-old. So I would most likely have a high residual value for normal shoe size people. Let's kind of label our equation. What does this value actually represent? Slope, very good. What does this value represent? The y-intercept. Now those are numbers for an equation, but this is real life. For homework, we're actually going to interpret what these values mean for the real life situation. What does the x actually mean? What is it representing? The age, very good, Danny. We plug in our age to actually predict what somebody's shoe size would be. It's a prediction model. Now the question says, after we've actually created our model, It says use this representation or this equation to predict the shoe size of somebody who's 8 years old. So I want you to use that model to predict the shoe size.
Wouldn't that be
5.58, so 5.5. You
Not any random age, but age do I give you?
what'd you get?
Yes, very good. So you're plugging in 8 to find the predicted shoe size.
Actually put it in.
Excellent. Now can you go show other people what you did? That is perfect.
How do you do that equation? How do you do that
Shoe size? So I'm giving you.
equation?
So what would you actually plug in? 8. Yes.
If that's what people
And it's 5.5.
Can you go show that group what you did?
Which one?
This one too.
Go, Sarah, you got this.
You took my calculator and it broke it. You broke it.
Predicted
Give him
shoe
$100,
size. Excellent. Can you explain to Jonathan what you did?
I really understand.
That can help you out. What'd you do? How'd you get that?
I cleared it, but I did 5. No, I did that. I pretty much did that and then 8. I got that.
Show me on your calculator.
I don't think it would. I did this,
So X is the age.
so that would be 8.
Yes.
Wait, hold on.
Is yours
4, 7. So that's 8. And then plus 1.82.
So that's your answer.
Oh, okay.
Should we round? 0.4.
Yeah, it's 0.47.
Yeah, I know.
So just being precise, attending to precision. What'd you get?
Are you serious?
Okay, I got it.
I just did 5.5 because that's in the common.
Hey, I gotcha.
Yeah, I got
No, I understand.
Lauren, what'd you get? 5.5. Okay, so looking at this, I was walking around in different groups. People were plugging in the age to the equation to find the predicted shoe size. Emily, what did you write down? What was your shoe size?
5.5.
She wrote down a 5.5. I get why she would do that. Is there such thing as a 5.58? No, not unless you're really famous and you can get a specialized shoe. So she rounded to the closest actual shoe size. That makes sense to me. But this isn't real. This is prediction. When I was walking around at first, I saw a lot of people put 7 there. Why would people put 7 there, Randall?
Because on the chart it says 8 equal, a boy at age 8 would be have a 7. But
Yeah, that's the real data point. Somebody out there who's 8 years old has a shoe size of a 7. This is how we can actually find the residual, the error. This isn't the real value. Please put a hat above the y. This is the number that we get from the equation. The residual equals the actual output, some true fact, minus the number that we get from the prediction model. So we know that the data point for an 8-year-old has a shoe size of 7, minus, according to our equation, we get.
0.58.
So what is the residual value?
1.42.
And what does this represent? What does this tell us?
Oh, how far away it is from the line.
That's the error. Very good. This is the error from the line to that actual data point. Max, can you come on up here?
Oh, God.
You're good. Can you draw in, not tell me the number values, but can you draw in the actual residuals for each data point? That is perfect. Explain what you did.
Well, this is how far, okay, this is the point and here's the line, the average line. So it's like obvious that you just gotta, I mean, this is how far the point is from the line. So I drew that, I don't know how to explain that.
And that's your residual. That's our error for every single data point.
This is the error. This isn't touching the lines, this is just showing how far it is from the line.
Very good. Which of those data points has the smallest residual value?
Probably, well, the one on the line right here.
Very good.
So
that
you would
has
be
the
like
smallest?
down here then, right, or something like that?
What?
Would you be like over here somewhere or something like that?
Yeah, I'm way out there. Now, is it possible to have negative residual values? Why? You don't know?
It feels like it should be.
If what? Say that louder, that's perfect, Sean. It's under the line. All the values, all the data points that are actually lower than our prediction line will have negative residuals. That's okay. All the points above the calculator are going to have positive residuals. Now, for our actual model, when we took the sum of our residuals, we got 5.3 repeated. That's like our sum of our error. If you had to predict what the summation of the residual would be for the best line of fit, what do you think that would be?
Wait, can you repeat that?
Yes.
Yeah, I'm sorry.
According to our calculator, this is the best linear model for this data. What do you think the summation of the residuals is going to equal? Take a moment with your group. What do you think?
Well, there's more negatives than positives.
Did you find an ID in here? Do you have it? Okay, can I have it?
What do you think?
We'll bring it to you tomorrow.
I have
No idea. I just guessed 4.
I don't really understand this.
Well, what does the sum of the residuals tell me?
How?
The average. No. Yes.
How much
Error.
error?
Oh.
Well, if it's the best model,
Oh, and that's just saying.
Wait, what?
0.
I was right.
I was like 4.8. I thought she was gonna give me some candy. I was like,
I have really no idea.
I mean,
I have no idea how
it's mine. I deserve this.
why do you think that?
I counted. Well, no, that, but if it's supposed to be the line of best fit and the calculator just does it right, then it should be.
Oh, it should be good, so when our error be less and less and less.
yeah.
I just follow along.
I feel like it's gonna be like the one or something or something.
Okay, at the bottom of your worksheet it says, this equation is considered to be the best, but let's talk about why. I had some groups up here talk about what the summation of the residuals would be. Danny, can you tell me what you said to me? Or tell the class what you said to me?
I didn't
What?
I didn't really say anything. It was.
Oh, it was Lene. Lene, what did you say?
The error would be 0
Why?
because it's the best line.
So when our sum of the residuals be less, our error, the less it is, the better our line is. Max?
Well, there's more negative plots, like, there's more that are under the line than over the line. Does that mean anything?
It does. I'm going to show you. These are all the residual values. I already calculated them. And you're right, I have 1, 2, 3, 4, 5 negatives. And I have 1, 2, 3 positive residual values. But looking at kind of like the absolute value, the negatives and the positives have the same or very close to the same value. So when I add them together, they kind of cancel each other out. They're making the error less and less and less from both sides. So when I add these all up, I get 0.08. Is that close to 0? Yes, it's really, really, really close. So according to what we did yesterday in the equation that the calculator spit out, what's better? Who had the better model, the calculator or the one we created?
The calculator.
Why?
Because it had a smaller residual value.
Smaller sum of residuals. In an ideal world, it would actually equal 0. Why do you think this one isn't exactly 0? What did we alter?
Oh, the slope and the y-intercept.
Very good, Max. Did we round?
Yes.
So our rounding adjusts our actual outputs a little bit. So if we didn't round, we would actually have a sum of 0. Yes?
So it's not possible to have all positive or negative residuals, right? Because then that means you do the line run. The line run.
Maybe one that we create, yes, but not one that your calculator
Why are
makes.
you
Because
close
that's
to
possible,
master?
right?
Very good. Okay, so that kind of sums up why our calculator, why that tool gives us the best linear model. But I have a different question for you. Looking at these graphs, these are 4 different scatter plots. Can all data be represented by a linear model?
No.
Yes.
I don't know.
No.
As a group, I want you to write down which graphs, 1, 2, 3, 4, which do you think can and which do you think can't, and tell me why. I'm going to pass around some sticky notes. That's what you're going to summarize on your sticky note.
Which can and
Yeah,
cannot
Marty.
Can.
Yeah.
Everything can.
I think it's just 3.
I'm assuming so if she gave you 4.
There's only 3 stairs.
So each person, write your name down and then tell me which ones do you think can and which ones do you think can't and why. You're just writing a short note to me. Can all data be represented by a linear situation? It's okay. I'll send out an email to the class. Just take 1 minute and write down your summary. What do you think?